Welcome back. As you are most certainly aware, we missed lab yesterday, which is very troubling to me because I was going to give this lecture in lab yesterday. And obviously we didn't get to do that. And there's the lab quiz, of course, that I can't count you as having to do the lab quiz. So I am going to sit down and look at the schedule and the lab and stuff and figure out exactly what we're going to do with regards to the lab, because I can't tell you, oh, we're going to come in on a Thursday and make up the lab. Right? That doesn't work either. So I got to figure out how I'm going to adjust the labs. But I just want to make sure you know that, yeah, these are things I'm thinking about. They're not like, things are fixed in stone and we're just skipping this lab, for instance. We may do this lab next week instead of, well, I think next week's a test. Is that right?
It's the week after.
It's the week after? Okay. Well, my point was we can't skip the test. The test will still come on the assigned day. And so, we'll have to look at things and figure out how it goes. So I will keep you informed when I make a decision on that. Right now, it's just letting you know, I will be making some adjustments because of the snow day. A second thing that's probably clear already is the homework that's due today was only covering capacitors, not covering Ohm's Law. I was going to cover Ohm's Law, like I said yesterday, and then we would have today's lecture, and the homework that would be due on Friday would be covering Ohm's Law plus Kirchhoffs laws. But we're not going to get to Kirchhoffs laws today, so it'll just be Ohm's Law for the everything.
This kind of goes back to the test. Are you going to make those like study guide sheets?
Yes, I will. Yes, I will. I totally should have done that on the snow day. I was like, snow day! And I didn't do anything. I did get a lot of puzzle work done and learned a little computer programming, but it's something, but I should have been working on classes.
No, you needed a day off.
Yeah, because it was so rough on Monday. I hope on Monday you guys took a few moments to think about the legacy of Martin Luther King Jr. And if you ever go to Washington, D.C., his memorial has some really great quotes. It's really kind of moving. All right, getting into the topic du jour. This will make sense by the end of the lecture. Electric current. Electric current is a fairly simple concept. Everybody knows a little bit about what water current means. If somebody says, ooh, there's a high current, what does that mean if it's water? What?
The rate of flow.
Okay, the rate of flow is very fast. Well, that's what we're talking about when we talk about electric current as well. Electric current is the rate of flow of charge. So we define current. Current has the symbol I, is equal to delta Q over delta T. Rate means per time, and the Q there is, of course, the charge. Delta Q over delta T is how much charge passes per unit time. So this picture illustrates we have an area that is circled in the wire, and it's measuring how much charge passes that area in a given second. So if we look at the units here, we have Q over delta T. What is the unit of Q? Coulombs, right. So we have coulombs, and what's the unit for time? So current has units of coulombs per second, which we abbreviate to an ampere, A for ampere. And of course, see, I have ampere written here, but we always say amps. So current is measured in amps. An amp is a coulomb per second. And I think I mentioned this the first day of this semester, that current, 1 coulomb per second, is actually the standard. Like second is the standard for time. The coulomb per second, or ampere, is a fundamental variable. So I probably should just say amperes because it's fundamental. And then the coulomb is defined as an ampere times a second. And that's a derived unit. Seems weird, right? Because charge is an innate property of matter. It seems that we would have a fundamental unit defining how much charge there is. But we have the ampere as the fundamental unit for reproducibility of the definition, which will come later. there is a confusion that occurs in current. Notice this picture shows Q traveling. Well, that's really pretty. But let's talk what really happens. In a real material, if it's a metal wire, what is it that's flowing when charge is moving through the wire? There's only two kinds of charge in our wire, protons and electrons. Which one's moving? Electrons. Well, electrons are negative charges. So what's actually happening is electrons are flowing in the wire. Well, with this definition, it implies a positive Q. And so if we have a positive Q moving to the right, what's really happening in the wire? What's really happening is electrons are flowing against that. And so this really concerns some people. When I was teaching at PUC, we had two electronics classes, the one I taught and the one that was taught by the engineering technology program. And the one engineering technology, they talked about electron current. And so the direction of their current was the direction the electrons were moving. Because, hey, what's actually moving? I taught conventional current, and I still do. Physics is always conventional current, just so you know. Like you get to the MCAT, it's going to be conventional current. Current defined as change in charge over change in time, which is the opposite direction the electrons are traveling. So when I draw a circuit diagram, I draw an arrow for the direction the current is flowing. There's nothing flowing the direction of my arrow. My arrow is showing a mythical direction because it's the direction that net positive charge flows, even though in reality negative charge is flowing the other direction. So why do I spend 2 minutes striding around in front of you talking about this? Because you might run into places where people talk about electron current. And it's important to connect the idea of current with what's physically happening. So that it's not like some bizarre, we say positive, current flows out of positive and into negative. And then when you start thinking about, but electrons, shouldn't electrons be going into positive? Yes, they are. Okay, this is actually something that's similar. This is going to now deal with current a little bit. Similar to one of your homework problems, we have a type of key, computer keyboard key. It's not the only type, but it's one type you can make. And this type of key has two conductors. So here's one conductor. Here's the other conductor, a plate underneath. So you have two parallel conductors. That's the fundamental basis for a capacitor. And then in between that, you have an insulator, as you see. But the thing is that insulator is flexy. So if you push down the key, it squishes. Well, what difference does that make if it squishes?
Plates can touch.
It's what?
Then the plates can touch.
Well, you're not going to push them down enough to touch.
Oh.
That would be a good answer, but it's not what happens in this design. So you push them down, it compresses. What does that do to a capacitor when you bring the plates closer together? Because it's epsilon 0 times kappa, kappa being the dielectric constant, something that tells you how good that insulator is at making an electron field, actually. Times area of the plate divided by the separation. As the separation gets smaller, the capacitance goes up. So when you press that key, the capacitance goes up. As the capacitance, and kappa will probably go up a small amount too, but we ignore that for this problem. So if the capacitance goes up, what's going to happen? Well, they put a constant voltage on that key. So you have something like 5 volts when you draw a battery is 2 cells. So here's some symbols for you. that equals a cell. Cells are chemical cells. They undergo a chemical reaction that will create a charge separation with a voltage difference that's on the order of 1 volt. 1 volt. It depends on your chemical cell what that voltage is actually going to be. If you buy AA batteries, a AA battery is not a battery, it's a cell, first of all. We just call them, back when I was a kid, we called things like C cells and D cells, which was correct, but we still said AA batteries. If you look at it, it'll tell you what the voltage is. And if you look at different batteries, you'll see they have different voltages stamped on them. That's because they're different types of voltaic cells. They're using a different chemical reaction, which gives you a different voltage. So you have a nominal value for the voltage of a AA battery, but they vary somewhat depending on the chemical reaction. So this is a cell. A battery is more than one cell put together. So this is a battery. It's a battery of cells. That's why it's called a battery, because you have a number of cells put together to work together. Now, when you look at these, notice one side is long and one side is short. The long side is the positive side. You don't have to put that positive sign because that indicates which side is positive by having the long side of your battery or cell. The short side is the negative. So when you look at the battery, you have positive, negative. That would be 2 cells. And that could be, some people write it with 3 cells. You'll also see it written. I've never seen it with more than 3 cells. So either of these is a battery. This one here is a cell. So it doesn't look like I'm adding them. And there are some textbooks, and I think ours is one, that uses the cell symbol for a battery, just to obfuscate things some more. So here I put a 5-volt battery. If the capacitance increases and the voltage is equal to 5 volts, what happens to the charge? The charge is going to go up. So what that means is that I am going to have mythical positive charge move from my positive of my battery onto the capacitor and move from the other side of the capacitor onto the negative of my battery. Now, if I have a charge flow, that means I'm going to have a current. And so you're going to have the current well, I'm just going to put V delta C over delta T. And so that current is going to have a value that depends on how much the capacitance changed and how quickly you press the key. So if you are looking at the current, which is what is done with this kind of keyboard, you see the current is 0. So we'll have current on this axis in milliamps. Time on this axis. The current is 0. Then all of a sudden you have like that. You have a spike here where the key was pressed, and a negative spike where the key was released. And so the keyboard actually is operated by looking for those spikes. So if you have that kind of key, if you have the patience of a saint, you could take a key and very slowly, sloth-like, press that key down and do it slow enough that it never detects that the key was pressed. I don't know why you'd do it, but if you had this type of keyboard, you could do that. So what's the point of this? To show a practical example of using a capacitor and how it can be utilized. Any questions about that key? It's kind of boring, I know. But it's a practical example. So now just to make sure we all followed along, when a capacitive computer key is depressed, what happens to the charge on the capacitor if voltage is held constant? It went which way?
I'm going to say increases.
That's because you're right. It increases because the capacitance increased, the voltage stayed, or the voltage stayed the same, so the charge increases. Now, capacitors in parallel and in series. This is in series here. Series means that you have them arranged one after the other. So look at that picture. Remember, that's what series means, one after another. When you have capacitors in series, now you have a homework problem that deals with this, but the homework problem leads you through without having to have this discussion first. In fact, if you've done this homework problem, you'll understand the concept I'm talking about. Let's say I started this with 0 charge on each one. So when I connect that battery, we'll talk about electrons now. Instead of talking about current, I'm going to talk about electrons. So what are electrons going to do when I connect that battery? I have a positive charge here. What does that do to electrons? They're attracted. So I have electrons that leave the top of the battery. Or excuse me, the top of the capacitor. Top of the top capacitor. Now what does the battery do to those electrons? The key thing is it doesn't store them. Batteries do not store charge. They give energy to charge. And so if an electron comes in, it's going to have to go through. It's just going to come out the other side with more energy. And so the electron goes through and comes out the other side and goes to there. So let's say I have 1 billion electrons leaves the top plate. It now has a positive charge. If it's only 1 billion, then it's going to be still 1.6 times 10 to the minus 10 coulombs. But it now has a positive charge because it lost electrons. And the bottom of the bottom capacitor now has an equal negative charge because that's where the electrons ended up. So I have to have this charge here and this charge here. Those have to be the same magnitude. It's just one is positive and one is negative because the electrons left the top of the positive side and they went to the bottom of the negative side. But then we're asked, what's the charge on a capacitor? Well, a capacitor stores energy in the form of either an electric field or a charge separation. So I'm going to focus on the charge here, a charge separation. The top of my capacitor is now positively charged, right? And what's that positive charge going to do to electrons on the plate below? It's going to attract them. So I'm going to have electrons that leave here and come up here. So I'm going to have electrons there. But those electrons left here are leaving this positive. And this positive has to match that negative because it was just electron motion. Charge leaves here, goes there. And then that chain reaction occurs again. And we have the electrons that are already spread over here. And so because it's just electrons moving from one plate to another, each one of these plates has the same magnitude of charge. And so the charge on each plate is exactly the same magnitude. Thus, we have Q1 all of them have to have the same charge. So if you have capacitors in series, that's the outcome I'm looking for right here. They have the same charge on each of the capacitors in series. It doesn't matter which capacitor is bigger or which one's smaller. They're going to have the same charge. Now remember, when I talk about the charge of a capacitor, I'm talking about the charge on one plate of the capacitor, because what's the net charge on the capacitor supposed to be? 0. Now you can do things in circuits to make it not that, but that's in a normal circuit, that's the way it should be. Net charge in the capacitor is 0. So this is not the net charge, it's the charge on one of the two plates. And we just take absolute value, that way it doesn't matter which plate you looked at.
I have a question.
Yeah.
So, given the battery next to it,
Yes.
why is it not negative on top and positive on the bottom? Like from the two leads, it makes sense. To me, it just seems like it would be opposite.
This is the positive terminal, right?
Yeah.
So as I focused on electrons, the positive terminal is going to attract electrons. So electrons leave here. If I have something with initial charge of 0 and it loses negative, it becomes more positive. Kind of like my bank account.
That's better.
Okay, so here is how the capacitors work when we put them in series. Now, sometimes we want to take a set of capacitors in series and say, well, can we just make one capacitor that does the same thing as these three? And the answer is yes, we should be able to. But if it's going to be the same, we're going to have the same relationship. So the relationship for a capacitor is Q equals VC, right? So if I look here, I have a certain charge Q that was moved across, and I have a voltage equal to the voltage of the battery for the entire set of capacitors. Now, if I look at each capacitor is going to have V1 is equal to there I was very generic. Q is equal to VC, so V is equal to Q over C. But of course, each one of these has the same charge. Q1 is equal to Q2 is equal to Q3 was my rule for capacitors in series. So that means I'm going to have, well, I'm going to do one more thing before I put it into an equation. This next thing actually requires us to use what's called Kirchhoffs Voltage Law. So I'm going to introduce Kirchhoffs Voltage Law here, even though technically it will come out of the lecture on Friday. Kirchhoffs Voltage Law says, since voltage is telling us about the energy per charge, if I go around a complete circuit, so I start somewhere and end the same place I started, I'd better be at the same energy per charge. It's kind of like saying, if I start at the base of, at Curry Village in Yosemite, and I take a hike and I go up the 4-mile trail, which is 5 miles long, to Glacier Point, and then I hike around the Panorama Trail another 10 or 11 miles, come back down. My elevation changes. I can add my elevation changes all the way through. But what I better have is I better end up at the same elevation I started. If I start at Curry Village and end at Curry Village, I better start at the same elevation as I end. Because my potential energy starting and ending is going to be the same if I start and end the same place. That's what Kirchhoffs Voltage Law says. As you go around the circuit, if you get back to the starting point, the sum of all the voltages is going to have to be 0. Because the voltages, remember, they're actually voltage changes. They're changes in potential energy per charge. And so we can take this and say that means that I have essentially, if I make a graph of voltage as a function of the position in circuit, I start at my negative of the battery, and I go to the positive of the battery, and it goes up to the voltage of the battery. I'm actually going to use the symbol we usually use. That E represents the voltage of the battery. Stands for electromotive force, EMF. And then if I go to each of my capacitors, so here's capacitor 1, capacitor 2, capacitor 3. When I get to the end of capacitor 3, I'd better be back to where I started. So here is the voltage for capacitor 1. Here's the voltage for capacitor 2. Voltage for capacitor 3. Now those voltages are voltage differences. The difference in voltage from one side to the other side of the capacitor. And this was the EMF. So I get a mathematical equation that says the EMF is equal to voltage 1 plus voltage 2 plus voltage 3. So using these equations, voltage subscript X is equal to Q over C subscript X. I'm going to have Q over C1 plus Q over C2 plus Q over C3 is equal to the EMF. So that's an equation that says if I add the voltages going around the loop, I better get back to 0. Notice I have my EMF was going up, and then each of the other voltages was going down. So I put them on the other side, equal sign. That's why they're positive instead of negative. Another way to have written that would have been that's right. So that's an equation that relates the voltage on my battery with the voltages across each of the capacitors. Note that the capacitors can have different voltages if they have different capacitances. Now for the equivalent circuit, this one here, it's very simple. The voltage from the battery is the charge on my capacitor here divided by my equivalent capacitance C sub S, S standing for series here, using the same equation, but looking at my equivalent. If it's equivalent, the charge has to be the same on both circuits, right? If the battery loses more charge in one than it does in the other, that's not equivalent. Battery loses was the wrong term. It should have been if the battery moves more charge in one case than the other. It's not equivalent. And so these Q's are equal. So what I have to have is that equation. And since Q is everywhere, I can cancel out the Q's and that's the equation for how capacitors add in series. Now you're probably thinking, that took a lot of time to do a derivation, and I know most students are like, what's the point? The point is going through and understanding how voltage, charge, and capacitance work together. That's the point of going through the derivation. The answer is something you're going to use, but the goal wasn't for you to be able to get to the answer, it's to see how those things work together. So this is how capacitors in series will add. So I can replace those 3 capacitors in series with one capacitor that's value is equal to what we get from this equation. Now, you have to be careful when you do the math with this. Notice it's 1 over capacitance series is 1 over C1 plus 1 over C2 plus 1 over C3. You can't just say like capacitor series is 1 over C1 plus 1 over C2 plus 1 over C3. That would be the wrong units and incorrect. Also note, if you're adding reciprocals, let's say you had 5 and 4 and 3. Okay, those are not easy numbers. Let's say you only have 2 instead of 3 to make life easier. and you have 1 and 1. If I have two capacitors, they're each 1 microfarad in capacitance, and I add them in series, I can have 1 over 1 plus 1 over 1, which is conveniently 2. So 1 over the capacitance in series is 2 divided by microfarads, which means capacitor series is 1/2 a microfarad. When you put capacitors in series, you're always going to end up with the equivalent capacitance being a smaller value than the smallest of the ones you started with. So putting capacitors in series makes for smaller capacitance. So if you have a couple big capacitors and you need something smaller, combining them in series will allow you to make something smaller out of the bigger ones. Now parallel. Nice job on my alignment of my fonts. I changed the size of the slide and didn't notice that. Parallel means that they have all of the tops together, and likewise all of the bottoms together. So in this picture, here are the bottoms. Those are all tied together with 1 wire. Now, something in circuits that's good to get in your head right off the bat is in electric circuit analysis, we treat wires as having no resistance. Resistance is a term that's coming up in like 2 slides. But what that means is a wire can be taken out and you can just put everything that's connected by that wire at one point. So I could draw my circuit with just this minus terminal and each of my capacitors coming off of that minus terminal. It's exactly the same capacitor or circuit. So I'm going to put here in blue everything that is tied together and is one location. Right? So all that blue is one location as far as the circuit's concerned. So the bottoms of each of those capacitors are tied together. Using the same rule, looking at the tops, top 1, top 2, top 3, all tied together. And so we have these things are in parallel because the tops are all tied together, the red, and the bottoms are all tied together, the blue. By the way, place where things are tied together we call a node. So I have here the red node and the blue node. Some people make mistakes, like on a test, they'll say, well, I have a node here because I had these 3 wires coming together, and a node here because I had these 3 wires coming together. Not so. Because these are only separated by wire, they're the same place as far as the circuit's concerned. So that's just one node. So there's one node on bottom, one node on top. Parallel because the tops are together and the bottoms are together. Now that we've established that these are parallel, I'm not going to do the math on this one. It's pretty simple. It's pretty simple mathematically. It's pretty simple conceptually. A capacitor, if it's a parallel plate capacitor, the capacitance is proportional to the area of the plates divided by the separation. If I have these capacitors connected like this, what I've done is just made bigger area on top and bottom, right? And so if I add up those, I should have a bigger capacitor now because I have bigger area. And that's exactly what you do. You just, basically, if you had identical separations, it would be the same as if you connected all the top plates together and the bottom plates together to make one big plate with the area that's equal to the sum of the areas. And so the equivalent capacitance here comes out to be the parallel capacitance is just the sum of the individual capacitances, which means that if you have parallel capacitors, the resulting capacitance is always bigger than the biggest one, since it's the sum of them all. So if you have some capacitors and you need to make a bigger capacitor, if you put them in parallel, you'll make a bigger capacitor. So I didn't go through the derivation here. It requires the same skills as the last one. Since we went through the last one, I presume you have those skills. the lead acid battery. I have this here so you can see what a battery really is. So lead acid battery is the type that you typically have in your car. Back in the day, you would put more fluid in your battery when the fluid gets low. These days they're sealed, except for as the case I mentioned last semester where I tried to take the contact off of the post and the whole post came out of my battery and spilled battery acid all over me. So with your battery, a lead acid battery, you have two plates, one that's lead oxide and one that's lead. And you have chemical reactions so that at the anode, you have lead plus sulfuric acid gives you lead sulfate plus hydrogen plus 2 electrons. So that's going to have a negative charge that's developed because of the chemical reaction. At the cathode, lead oxide plus hydrogen sulfate. So this hydrogen sulfate and these hydrogen ions move through, and those will produce, taking 1 electron, lead sulfate. So notice that both your anode and cathode are becoming lead sulfate over time. But at one, each reaction absorbed an electron. At the other one, each reaction produced 2 electrons. And so what you're going to do with these two coupled reactions is the reaction will go until you reach a balance between the electric charge and the energy required to make the reaction go. And so you end up with a positive and a negative electrode called the cathode and the anode. If you connect something to the battery, you'll have electrons fly away from the negative, electrons pulled into the positive. If you have a complete circuit, circuit means that you have a path that goes in a loop, right? It doesn't go to nowhere. It's not a bridge to nowhere. It's something that goes in a loop. So if you have a complete circuit, those electrons that are pulled off or that leave the negative will be pulled into the positive. And then you have current that will flow through the circuit. But as soon as charge starts to flow, then your equilibrium in the battery is broken and the chemical reaction has to start up. So the battery, the battery should have its full terminal voltage, but as soon as you start to use it, the chemical reaction has to start up, and then your battery can only supply current at the rate that the chemical reaction can occur. So you get a limited amount of current from the battery. And as the chemical reaction is going, the chemical reaction only starts when the voltages drop. When you have the voltage difference between the two is smaller than equilibrium value. So as soon as you connect it, the voltage for the battery should drop. That's the way batteries work. So when you test a battery, one of the things that a naive person does is just takes their multimeter and checks to see what the voltage across the terminals is. What the voltage is across the terminals. Well, the terminal voltage should be the full voltage unless your battery is completely shot. But if you're using the battery, if the battery is in good shape, the voltage won't drop very much when you test it in use. If it's in bad shape, the chemical reaction can't work quickly, right? With this battery, if both those plates are now a high amount of lead sulfate, your chemical reaction is not going to work very effectively anymore. And so the chemical reaction will work much slower, which means the voltage is going to drop much more when you're using the battery. And so for checking the battery, you actually want to check what the voltage is under load to see how much it's dropped. So checking it not under load, not really that useful. If your voltage is not full voltage when it's not under load, you know that battery's completely and utterly shot. And by the way, since Nathan has killed 2 batteries in the last 6 months, actually the last 3 months, what happens when you kill the battery completely? Basically, you have 2 plates of lead sulfate. At that point, there's nothing you have to do. The normal charging a battery reverses the chemical reaction so that one of them is going to build back to lead and the other one's going to build back to lead oxide. But once you have 2 lead sulfate plates, it pretty much is done. There's an electrical fault in this car. I know, Nathan's like, did you really have to talk about this? Resistors and Ohm's Law, the topic of lab yesterday. Yeah. So Georg Ohm, I just love to say his first name, noticed that for many materials, not all materials, but for many materials, there was a linear relationship between the voltage drop across the material and the current going through the material. So first is, he called these things resistors that behave this way. Resistors are drawn straight line, change to black, straight lines all the way through. Now, I am just as lazy as anyone else out there, so I often don't draw them with nice, careful, straight lines. But it is important when we get to talking about inductors and coils. Inductors or coils look pretty much the same except for they're curvy instead of straight. And so if you're not careful, it's hard to tell the difference. So that's the symbol we use in circuits for a resistor. And what Georg Ohm noticed was, if this side is positive and this side is negative, and current is measured going like this, so current is measured going from the side we designate as positive toward the side we designate as negative, then there's a linear relationship that says the voltage difference between the positive and negative is equal to the current, which is the current going through the resistor, multiplied by this resistance value. So something with more resistance means for the same current it's going to have the higher voltage. Less resistance for the same current, lower voltage. Of course, in most cases, we're using something like a battery, and you take the current. For the same voltage, if it has more resistance, it's going to have less current. We can add resistors in series or parallel. I'm actually not going to do the derivation today. It's a parallel derivation to the one we already did with capacitors in series and parallel. And so I'm just going to write the results here because of time. So the resistance, not voltage. The resistance in series is equal to R1 plus R2 plus R3 plus R4, etc. The resistance in parallel I ran out of space. So 1 over resistance parallel is equal to the sum of 1 over resistances of each parallel resistor. Do those look like the capacitor equations? More or less. They're reversed, though, in terms of series versus parallel. Series resistance is bigger than the biggest total resistance because they're adding, whereas capacitance was smaller than the smallest. Parallel, you add reciprocals, and then your parallel resistance is smaller than the smallest resistor you started with. So we can add resistors in series or parallel to get an equivalent resistance as well. So we should probably do something like that. First thing is trying to identify relationships. So this is showing a process, not with numbers, but just with concept. So you're given this starting circuit. The starting circuit has 1, 2, 3, 4, 5, 6, 7 resistors in it. And it asks you, what's the total resistance? The first thing you have to identify is what's in series and what's in parallel. And of course, this picture has it all worked out for you. It circles, first, you have these 3 things are in parallel and these 2 things are in parallel. So we can combine those to find the equivalent resistance for each one. And so that's the first step. And then after you've done that, you say, wow, these 2 equivalent resistances that I just found, now those are in series with each other. Now, if you go back to the first picture, R2, if you compare R2 and R5, what kind of relationship do you have? It seems like it would be series. So here is another addition to the rule on series. If it's series, they have to be sequential. Sequential with no alternate path. So what that means is if I have a resistor like this, and then the circuit goes on, if I have current that goes through this, it could go like that, or it could go like that. It has two paths. So even though this resistor here and this resistor here are connected top to bottom, because there's an alternate path that the current could take, those are not in series. They're also not in parallel. So resistors don't have to be series or parallel. They can be series, we like that. They can be parallel, we like that too. Or they can be something else. Well, that takes a little more cunning. So when we look at this picture, even though those two would seem to follow the series relationship, they aren't in series because I could have current go like that as well. Right? The current could go either way. So that's why these here, these are truly in parallel because the tops are all together, the bottoms are all together. Now, there's no option, but current that goes through one has to go through the next. So these are now in series. So we combine those in series. Now, if you look over here, what about this and this? Are those series?
Or are they both R1? Or is one R7?
They are. It is R7 actually. Yeah.
Okay.
It's a very good question. Are those in series?
No.
No. Why not?
There's two paths.
There's two paths, right? That's a first thing you have to be able to identify. Identify if it's in series or if it's in parallel or if it's neither. And so that is neither, so that's why nothing has been done with it so far. But since these two are in series, they're combined, and now these tops are connected together. These bottoms, I know I shifted what colors on top and bottom, doesn't matter to me, are connected together. So these are in parallel. We combine those in parallel. Then these are in series. And so we can shrink it down to one resistor. So we can take this entire circuit and shrink it down to one resistance. And the question you should ask now is a very fundamental question. Why? Why would we do that? Well, here is the fundamental reason why. We want to know if I connect my battery to this, how much current is it going to draw? With the circuit we started with, that real complicated circuit, okay, zoom, there we go. With that circuit, I can't tell you an answer. I just can't. But after we've done all this work and we have it down to one resistor, I can. Now that we have it down to one resistor, I can say, well, my current that it's going to draw is going to be the voltage of my power supply divided by my, what is that, RS. It has RS prime there, so that's what I'm putting, RS prime. Now I can tell you what the current's going to be. Once I've calculated that current, then I come back to my original circuit and I can say, well, I have that current going through here, and so I can calculate what the voltage drop here is. And so that means I can calculate the voltage here by taking the voltage from the battery minus that voltage drop. And then I can determine how much current goes here by taking that voltage difference in this resistance. And if I come to here, I can calculate, well, I can actually take the difference and calculate the current, but then I have to come to here to calculate the voltage drop across there. And so I can go backward through my circuit and calculate what the voltage drop across each element is, what the current through each element is. In circuit analysis, that's what we're generally trying to do. Find the voltage and currents everywhere in the circuit. So the reason to combine the resistors in series and parallel is so we can find the current and work our way back and find the currents and voltages everywhere in the circuit. So it's not to give you busy work. In fact, nothing in this class is to give you busy work. Speaking of busy work, remember, it's not busy work. It's supposed to be fun work. The scrapbooks, you should be working on those so that when we get to our test, you have the scrapbook ready and you don't like the night before say, oh no, got to put two, Right?
Right.
Right. Have a great day.